Hey there, chemistry people. I'm here. I'm going to talk a little bit about kinetics, give you kind of an overview of probably the first half of what we want to study in kinetics, which is the lion's share of it. I'm just going to do a little bit of an intro, kind of like I've done in class, just something that you can look back on and think about a few times over. So there are four basic things that affect the rate of a chemical reaction. And so the rate of a chemical reaction could be affected by, well, maybe one is going to be concentration of the reactants. Two, temperature. Three, the presence of a catalyst. And fourth, surface area. Now, these four factors affect the rate of a chemical reaction, how fast it happens. We haven't thought a whole lot about how fast it happens. We've made decisions on if reactions happen or not, but we haven't really talked about the time frame with which reactions happen. Some happen very quickly, some happen very slowly. Things that could speed up a particular chemical reaction would be maybe changing the concentration, changing the temperature, adding a catalyst, or increasing the surface area. So let's just take a brief look at the concentration of the reactants. If we were to look at the concentrations of reactants here, and here I have my lovely beaker that I enjoy, and I have a hypothetical reaction. A plus B gives you C plus D. And I have a whole bunch of A's sitting in my beaker and a whole bunch of B's. In fact, 5 of each, right? Now, the likelihood that this reaction happens is directly related to A coming in contact with B. A and B have to touch one another. If A and P don't touch one another, well, then there's no way for A and B to react. And so in this situation, A and B, they're both sitting there, so the two of them have the opportunity of reacting, right? However, when A and B react, say we have this A and this B come in contact, and you've seen me do something similar to this, right? What do we end up with? We end up with C and D. And this could keep on happening. And so we lose another A, we lose another B, we lose another A, we lose another B, we lose, say, an A, and we lose a B. And what we end up with are a whole bunch of C's and D's, and C and D, and C and D. And you're getting the picture that now I only have one A and one B left over. Well, the likelihood of A and B coming in contact are relatively slim. We had this discussion when we talked about why we need an excess reactant in a chemical reaction, right? Well, remember, contact between A and B is imperative for this reaction to happen. So by increasing the amount of A or B, we could affect how fast the reaction goes to completion in this situation. Or we could affect how fast the reaction happens overall. For instance, let me put my A's and B's back. We're moving backwards. And now suppose I was just to say, all right, I could speed up this reaction by just adding a bunch more A's. Because what are we doing now? If I increase the amount of A, which is increasing the concentration, because I'm increasing the number of A's per unit area, the likelihood of A and B to come in contact is just becoming greater and greater. So A and B now have a much greater likelihood of coming in contact, and I've perhaps sped up this chemical reaction by increasing the concentration of one of the reactants. I could have just as likely done the same thing with B. Now, by increasing the concentration of the reactants, I can speed up a chemical reaction. It's one of the factors. And we're going to focus on that factor quite a bit. Other factors can affect this. However, there's one that is really important. We spent a lot of time discussing the changes in concentrations of reactants. If we look at the temperature, well, temperature is directly related to speed. And you might remember this because in gases, and some of our reactions happen in the gas form, we have the mu RMS, and that equals the square root of 3RT over the molecular weight. Well, this equation gets us the velocity of the particle, and it's directly related to temperature. It's the only thing that can change in this particular reaction. So if we increase temperature in this equation, we can increase speed. If we increase speed, the things could heat each other more intensely. We could have something that might overcome the activation energy more. Now we'll spend more time talking about activation energy as it relates to the catalyst as well, and as well it relates to surface area. So these other three we'll spend more time talking about when we nail down more of the details of the concentration, because the lion's share of our mathematics is associated with changes in concentration, in interpreting concentration. So we're going to go right into talking about concentration and rate in general, and then we can talk about those other aspects a little bit later. So now let's take a look at just what rate is overall. Suppose I want to talk about what the heck is rate. Well, let's think about the rate that you're most familiar with. Traveling in a car, miles per hour, right? And so if you're traveling in a car and you look at your speedometer, you'd have a certain number of miles in 1 hour. And what do we have but a unit of increment in the numerator, in this case a distance, over a unit time. And so we want to know how much per unit time. And in a velocity or in your car, miles per unit hour. And how far did you go in a certain period of time? Well, here with our chemical reaction, we're interested in how many particles react per second. Well, the best way to figure out particles per second instead of doing moles per second is to do it in a finite container. And so we can do changes in molarity per second. So our unit of, well, change is delta molarity per second. And so sometimes that delta sign, it means changes in molarity. And that's usually our unit. Now what I have here is a concentration versus time graph. And this is just a straight graph showing changes in concentration versus changes in time. And you'll notice that what happens to it, we start off and then this slope sort of evens out, right? Now, this kind of goes hand in hand with my previous slide with the A's and B's, right? And because, well, when you have a lot of A's and you have a lot of B's, and suppose I draw a few more B's in there, right? In the beginning, just to make the A's and B's a little more equal. In the beginning of this reaction, I have a whole bunch of A's, a whole bunch of B's. And remember, as these things react, they become product. And so they technically disappear. Oh, B and A, there they're gone. B and A, now they're gone. A and B, now they're gone. B and A, a reaction. Now, as the concentration of the reactants gets smaller, the reaction slows down because the likelihood of them coming in contact diminishes. And so when we look back at our graph of reaction rate, at the beginning here, where we have our first part of our graph, we have this really steep slope. And then the slope evens out over time because the concentration of our reactants gets smaller and smaller, and the likelihood of them coming in contact with one another diminishes. Now we could find out the instantaneous rate by finding the slope of any one of these points by creating a triangle like so. And here this image is showing us how to find the rate at any one given instant on this particular graph. And so we could find out the rate by using a tangent line that's associated with the slope of this curve. And that would allow us to figure out what the instantaneous rate it was at any given time. Now, if we were to look at a graph maybe a little bit more elaborate, and this graph itself showing us what? Hydrogen iodide. I can write a chemical reaction for this. It's showing us the concentration change of hydrogen iodide, hydrogen plus iodine yielding HI. So this is a balanced equation for what they're showing here. And notice how HI is increasing. Whoop. And it's increasing and it's evening out kind of similarly to the reactants doing their thing. And so this is showing us some reactants and some products. And so here's our reactants and here's our products. And so as reactant concentration goes down, product concentration becomes larger. Each of them approach a horizontal line as the reaction slows down. So initially we have some very fast rates, and then that rate diminishes over time. And the reason is the likelihood of the reactants coming in contact with one another. It affects how fast this reaction might happen. And so now notice how the concentration of those reactants affects the rate. We go back to our picture and notice as I start to get rid of more A's and B's, eventually we get to the point where this reaction happens really slowly. Because now we have several B's. Now I pumped up the A's initially, but imagine we only had a couple A's and a B in here, right? But now here's something that's missing from my picture that I might want to add. They say we have an A and a B, but now remember, what's filling this thing? C, D, C, D, C, D. There's C's and D's everywhere. So the likelihood of A hitting B, they're not floating around in an empty container. They're bouncing into C and D continually. So they've got to bump into each other a million times before they actually might bump into A. And so even though there might only be a few things in a container, we have to remember that the products are filling that container, or the products are part of the scenario here, and they affect this likelihood of A coming in contact with B. They do. Now we're going to hit some mathematics, but I'm going to stop this and come up with a second installment, so this is a very emailable file. Hold on to your hats. Soon will be part 2.